Hello, Honors Algebra 2. Today we're going to do Edgenuity section 10-6 called Binomial Distribution. We've got three objectives here: to identify a binomial experiment, to identify the probability of success, probability of failure, and number of trials for a binomial experiment, and to calculate binomial probabilities. So let's take a look at our first problem. And the first problem really involves the definition of a binomial experiment. So, which three criteria do binomial experiments meet? So, there are only two trials. Well, whoops, sorry about that. You might think two because of the bi in binomial, but that's not really what we're talking about when we talk about binomial experiments. It's not that we just do two experiments, two trials, and we're done. This is not, I mean, think if you only did two trials of anything, it would not really make a lot of sense, right? So, definitely not two trials. Well, that leaves us with only three criteria, but let's talk about them. There are only two outcomes per trial. Now, that is exactly what we mean by a binomial experiment. What we mean is that there are only two outcomes, and I'm actually going to star this one because it turns out that this is actually the most important part of the definition. The rest of it can kind of be to any experiment, basically, but two outcomes, only two outcomes, exactly two outcomes for every trial. Like flipping a coin, you can only get heads or tails, or being specific about, I only want to consider when this happens or this happens. Being under or over a particular number, things like that are binomial, okay? Each outcome is repeatable. Depends on what you mean by repeatable. I mean, you could certainly get either outcome each time, but that doesn't necessarily mean that every outcome, that every set of trials is going to be the same, that sort of thing. So I'm gonna not choose that. It does say three criteria, but I'm gonna not choose that one for right now. And then D, the probability of success is the same for each trial, and that absolutely has to be one. Okay, it doesn't really matter what the success is. So for example, we're going to run into some problems here that are rolling a six-sided die, and we can have binomial experiments with a six-sided die. It's a little more straightforward with, say, flipping a coin, right? If I flip a coin, there's only two possible outcomes, heads or tails. And there's a 50% chance of each one. But if I roll a six-sided die, there are six possible outcomes, unless I get more specific and I say, I want to roll a 5. And then I either rolled a 5 or I didn't, right? And those are my two possible outcomes. And possibility of rolling a 5 is 1 out of 6, and possibility of not rolling a 5 is 5 out of 6. So they have to have the same probabilities each time. That is, if I say I want to roll a 5, the chances of rolling a 5 have to be 1 out of 6 every single time. But it just has to be something. It doesn't have to be that it's like 50% every time. I hope that makes sense. All right. So again, this one maybe, but depends on what you mean by repeatable. All right. So I'll give you a moment to look at that, ponder that. And let's move on to our next question. Uh, which of these qualify as binomial experiments? Okay, so again, we gotta remember what binomial means. It means two possible outcomes, right? So a survey asking 50 people their favorite food. How many possible outcomes are there to that? If I ask 50 people what their favorite food is, and I don't give them any choices, I might get 50 different foods, right? I might get some things that aren't even food. Some people might say, well, I like juice. And then you go, but that's not a food. And I go, I don't care. That's my favorite food. and there's certainly not two outcomes, right? I mean, even if one person says pizza, another person says macaroni and cheese, and another person says lasagna, that's three already. Those are some great foods. So if I just ask their favorite food, certainly it's an experiment. It's just not a binomial experiment, right? A survey asking 50 people if they like pizza. So now really the question should be a little tiny bit more specific than that. Actually, it should be way more specific than that. But the idea is you should only be able to give a yes or a no to this, right? And maybe it's that I'm only accepting yes or no answers to this. Do you like pizza? Yes or no? Really, for this to be a really good binomial experiment, it would be like, do you like the hot and ready pepperoni pizza from Little Caesars? Yes or no? But yes, this is a binomial experiment. Granted, maybe one not designed all that well, but we won't quibble over that part. I measure 50 people to see if they're over 6 foot tall. Well, so what are the possible outcomes to that? I measure you, and you either are 6 foot tall or less, or you're over 6 foot tall. That's a yes or a no. So that, too, is a binomial experiment. And then finally, rolling a number cube 50 times and recording the results. Number cube is a 6-sided die. But if I just roll it 50 times and record the results, I'll get some 1s, some 2s, some 3s, some 4s, some 5s, and some 6s, presumably. So this one, definitely not. So those two in the middle, B and C, those are the two that are binomial experiments out of this. All right? So I'll give you a moment to look at that, ponder that. And let's move on. All right, so up at the top here, I am giving you the expression for calculating probability of a binomial experiment. Okay, we've got this part, which is set as n choose k, n choose k, and it equals this. Those exclamation points are factorials, not command points. And we'll talk about what a factorial is as we go through this. So what are the values for n, p, and k? And we're going to talk about what n, p, and k stand for, what they represent. For this question, what is the probability of getting exactly 5 heads in 10 coin flips? And then find that probability, okay? So let's talk about what these mean. N is the number of trials. The K is the number of successful, or the number of the number of successful trials that we want to get out of this. And P is the probability of a success. Okay, so let's talk about what each of these are for this specific question. Okay, that's an awful N there. So how many trials do we have? Well, we read through the problem, and it says, what is the probability of getting exactly 5 heads in 10 coin flips? That's the number of trials. We're going to flip a coin 10 times, so N is 10. Okay? How many successes do we want? Well, a success is getting a heads, and we want that to happen 5 times. So K is 5. And what is the probability of success? Well, what's the probability of getting heads on a coin flip? As long as the coin is fair, it's not weighted to land on one particular side or another, that probability is 50%, right? Or 0.5, or 1/2, 1 out of 2. And because I'm going to be doing these calculations by hand, I'm going to wind up using the fraction, because fractions are easier to do calculations by hand with than decimals usually are. So as long as they're fairly simple fractions. All right, so I'm going to erase I'm erasing these definitions of the letters, and we'll just have what they stand for there, and let's calculate the actual probability. Okay, so I need that N choose K part. So the N is 10 factorial, and I'll talk about what that means in a second. And then K factorial, that's 5 factorial, and N minus K is 10 minus 5 factorial, times P, which is 1/2, raised to the K power, raised to the 5th, times 1 minus 1/2, raised to the N minus K power. So there's all my numbers that I need. So now let's take a moment on the side here, talk about what like 5 factorial means, what a factorial means. Okay, so there's 5 factorial, 5 exclamation point. What that means is 1 times 2 times 3 times 4 times 5. And 10 factorial means 1 times 2 times 3 times 4 times 5 times 6 times 7 times 8 times 9 times 10. So that's what a factorial is. Okay? Let me erase that. And because of that, I can do some clever stuff with this fraction. Notice that I can boil this down to all multiplication, which means I can do some canceling between top and bottom, right? So here's what I'm going to do. I'm going to very cleverly split up that 10 factorial so that I can do very simple cancellation, okay? So 10 factorial is 1 times 2 times 3 times 4 times 5 times 6 times 7 times 8 times 9 times 10. Notice that at the beginning of that, I've got 1 times 2 times 3 times 4 times 5. So at the beginning, I've got 5 factorial. So the way I'm going to split this 10 factorial up is I'm going to do 10 factorial is 5 factorial times 6 times 7 times 8 times 9 times 10 over, and then I've got 5 factorial there, and then 10 minus 5 is 5, so I've got another 5 factorial there. But look at, I can cancel the 5 factorials, because that's just the same set of multiplication twice, right? Once on the top, once on the bottom, meaning I can cancel it. And instead of writing this 5 factorial as 5 factorial, I'm going to write it, and instead of writing it as 1 times 2 times 3 times 4 times 5, I can actually eliminate the 1, because 1 times anything is itself. So I can call this 2 times 3 times 4 times 5. And that allows me to do more clever things, like say I could take this 2 times 3, which is 6, and cancel the 6, right? I could take 8 over 4 and call it 2, which I'll do later. And I could take 10 over 5 and call it 2. So I'm just trying to simplify things as much as possible. Okay? Then I've got 1/2 to the 5th. Well, 1/2 to the 5th, let me show you a little more side work here. If I have 1/2 raised to the 5th, what it means is 1/2 times 1/2 times 1/2, 5 times. And that, and you do top times top, bottom times bottom. So 1 to the 5th is 1 times 1 times 1, 5 times, which is just 1. And then on the bottom, I've got 2 to the 5th. And so I'm going to write it that way. And that is going to allow me to do some clever stuff later. Okay? So just so you're aware that that's why I'm writing it that way. And then finally, what's 1 minus 1/2? Well, it's 1/2. And then it's to the 5th, right? 10 minus 5, so this is 1 over 2 to the 5th again. So I'll just write it that way. Okay? So then finally, we're sort of getting to a point here. 8 over 4 is 2. 10 over 5 is 2. So I've gotten rid of everything on the bottom. And then at the top, I've got 7 times 9 times 2 times 2, which I'm going to write as 2 squared, because I've got all these 2's on the bottom that I'll be able to cancel some stuff, okay? Over, all of this stuff on the bottom is gone. So I've still got this stuff on the bottom. That's 2 to the 5th times 2 to the 5th is 2 to the 5 plus 5, or 2 to the 10th, which allows me to cancel the 2's up here with 2 of them down here and make it to the 8th. So I've got 7 times 9 over 2 to the 8th. And if you figure out 2 to the 8th, that winds up being 64, right? Yeah. Let me double check that and be sure. 2 to the 8th is what? That's 4 to the 4th? Yeah, so no, it's not 64. 2 to the 8th is what? That's 4 to the 4th, which is 16 squared, which should be 256, I think. That sounds more like it. Yeah, that sounds a lot more like it. And anyways, whatever 2 to the 8th is, and then 7 times 9 is 63 over 2 to the 8th, or 256, and then you do this and you get a decimal for it. And, excuse me. And so this, whatever you get as the fraction when you put it into a calculator, I'll let you do that part on your own, is the probability. All right, so I'll give you a chance to look at that, ponder it. And let's look at the next question. Next question, calculate the probability of rolling a 5 exactly 3 times. So here's something that we know in 10 rolls. So let's line up what our variables are. Our n is 10. We're going to roll the die 10 times. We want to get a 5 exactly 3 times, so the number of successes that we want 3 successes. And the probability of 1 success of rolling a 5 is 1 out of 6. So this is the scenario I was talking about a little bit earlier. Okay. The chances of success are not 50%, but it's still a valid chance. Okay. Excuse me again. So let's plug that all in. Let's go back and double check things. We need n factorial, 10 factorial, over k factorial, so that's 3 factorial, times n minus k factorial, so 10 minus 3 factorial, times p to the k power, p is 1 over 6, k is 3, times 1 minus p, so 1 minus 1 over 6, raised to the n minus k power. So there's everything we need to calculate. Then all we have to do is actually calculate it, right? It would be helpful if we figured that out in side work. 1 minus 1 over 6. 1 as sixths is 6 over 6. Minus 1 over 6 is 5 over 6. So that'll help us. I'm going to do the same thing with this 10 factorial. I'm going to call it 3 factorial times 4 times 5 times 6 times 7. Well, no, you know what? Let me be more clever than that. Let me call it 7 factorial. 7 factorial, because I'm going to get a 7 factorial right there, times 8 times 9 times 10, because I'll get a bigger cancellation that way, right? Over 3 factorial, which I'm just going to call 2 times 3 for right now, times 7 factorial. And then the 7 factorials will cancel. And then I can figure out some clever stuff with this. I can do 8 over 2 is 2, and 9 over 3 is 3, or something I could have done 10 over 2 is 5. It doesn't really matter, but I'll deal with those cancellations a little bit later. And then I've got 1 over 6 raised to the 3rd power, which is the same as saying 1 over 6 to the 3rd power. And then I've got 5 over 6. We figured that out here. 5 over 6 raised to the 7th power, which is going to be 5 to the 7th power over 6 to the 7th power. And then we're going to see what we can get out of it. So 8 over 2 is 4. 9 over 3 is 3. And then times 1 is just that, times 5 to the 7th power, whatever that is, over, I've taken care of the 2 and the 3, so 6 to the 3rd times 6 to the 7th is 6 to the 10th. And I might do some clever stuff with that, but mostly you'd probably just put this into a calculator and get an answer. A good calculator to use for something like this is an online graphing calculator called Desmos, which you can find at desmos.com. Really, really good for doing calculations because you can actually make the calculation look exactly like this in Desmos pretty easily. You can also graph some really cool stuff in Desmos, so really handy, useful tool. So I'll give you a chance to look at that and ponder it. Let's move on to our last problem for this section. Okay. To pass a quiz, you have to get at least 7 out of 10 questions correct. The probability of guessing a certain number of questions correct on a multiple choice test are the following. Okay, so, and there are the numbers. What is the probability of passing? So you can get 7 right and pass, or you can get 8 right and pass, or you can get 9 right and pass, or you can get 10 right and pass. So we want 7 right, or 8 right, or 9 right, or 10 right. And every or in probability, maybe with some more involved calculations, but every time you say or and you're talking about probabilities, you're going to have to add. Okay? So saying 7 right is saying take into account the probability of 7 right, and this is just guessing, right? Or plus, we'll add the probability of getting 8 right, or the probability of getting 9 right, or the probability of getting 10 right. So all we have to do is take all of these numbers and add them together. So that looks like 0.0031 plus 0.000386 plus, and then we've got this, and you got to know how to deal with that. To convert 2.86 times 10 to the negative 5th into a decimal, you find the decimal, and because of the negative, you're going to move it smaller, that is, so that the number gets smaller this many times. So 2.86, and move it so that the number gets smaller 5 places. 5 places smaller. 1, 2, 3, 4, 5. So the new decimal is here, and fill with zeros. So that's 4 zeros. So 0.000286 plus, and let me erase this one because we got to do it again for the probability of 10. So 9.54 times 10 to the negative 7th is 7 spaces smaller. 1, 2, 3, 4, 5, 6, 7. And I know most teachers don't talk like that. They say, oh, move it to the left or move it to the right. And the reason I don't talk that way is because when you start talking smaller and bigger is something that you can talk about going either way. If you start talking left and right and that sort of thing, you have to adjust in which direction you're going. But if I know I'm going to have a small number, it's always a small number. I just got to know how to represent it. If I know I'm going to have a big number, it's always a big number. I just got to know how to represent it. So that's why I talk in terms of small and big. So 1, 2, 3, 4, 5, 6 zeros here. Let's see if I can squeeze that in. 1, 2, 3, 4, 5, 6, 9, 5, 4. And then take out a calculator, or you get on Desmos, and you add all those up. And I suppose we can do this one. I'll get out my calculator. And let's see, 0.0031 plus 0.000386 plus 0.4 of them this time. 1, 2, 3, 4, 2, 8, 6 plus 6 of them this time. 1, 2, 3, 4, 5, 6, 9, 5, 4. Which gets us 0.003, let's call it 52. Let's just round to that many decimal places. Which I could also write as a percent would be 0.352%. So if I wanted to pass this class or this quiz just by guessing, I only have a 0.35% chance of doing that. Not real good, right? As opposed to, like, if you study, give yourself a much better chance, right? All right. Well, thank you. I hope this has been helpful. Thank you so much for listening.